Hey, good morning. Calculus 2, Chapter 10.4, polar coordinates. We got started on this with a video the other day. We got this triangle that relates the x's and y's, the old rectangular coordinates, to the new r and theta polar coordinates. So this point can be represented with an x-y coordinate system, or it can be represented with an r theta polar coordinate system. By the way, this triangle I drew, is just a right triangle, and these relationships fall out of it, which are pretty basic relationships. Maybe you should memorize, or there they are in the triangle. And that triangle could be sitting in any quadrant. I mean, this point can be anywhere in any quadrant, but I drew that picture. But then that picture yields these equations, and these equations help me convert back and forth, and I did a little of that in the previous video. We did this one. X squared plus y squared is 9. We all know that's a circle, radius 3, centered at the origin, and its polar coordinate equation would be converting it. I would take the x squared plus y squared, change it to an r squared, take the square root of both sides and write r equals 3, and that's what I got, a circle, radius 3, centered at the origin. So that's cool. And so circles have this very nice, simple polar coordinate equation. Let's try another one. This one's interesting. So with the minus sign in there, all of a sudden, this is actually a hyperbola. I didn't do much with hyperbolas, but this is a hyperbola. I don't really care. I wanted to show you, practice the converting here with you. So I don't have the plus sign. I can't do this formula that I just used. So let's replace the x with an r cos theta, and then it is squared. Let's replace the y with an r sine theta, and it is squared. And in a way, when someone says, please convert this into polar coordinates, we're done. We did. We shouldn't be done. I told you the other day we should solve for r, maybe, or simplify this somehow. So watch this. If something interesting happens here, that's r squared cos squared. That's r squared sine squared. If you factor out the r squared, you have cos squared theta minus sine squared theta. By the way, if I would have done the same thing up here, that would have been plus, and if it's plus, what is cos squared plus sine squared? It's just a 1, and I would have been right here. So you could have done that to this, and you could have, anyway, it all works. But with the minus sign, that's not a 1, but it is another identity. It happens to be this identity, the cosine of a doubled angle, the cosine of 2 theta. So this turns into cosine 2 theta equals 9. So this is kind of an identity. So that's cool. That helps simplify it. Let's see. I don't know. What if you divide by this? R squared, again, I'm trying to solve for r. I might be stretching it a little. That would be a cos 2 theta in the denominator. What if you took the square root of both sides? I guess r would equal a 3. I guess I could move that cosine up. It would be a secant. So I would take the square root, and I'd have 3 times the square root of secant 2 theta. That's pretty weird, but that technically, I think, maybe I do need the plus and minus on this since I'm square rooting that. Anyway, that should give me this hyperbola I was discussing. But anyway, I just wanted to show you some of the moves, some of the identities that might be useful. There's another one here. So I'm going to get rid of this one. I like that move there. This one's kind of cool. Let's see what happens here. Let's see. Actually, I'm sorry. I think I want that to be a 0. Okay, check this out. So now, if I grab the x squared and y squared, I can add them together. What is x? I can convert that. That's an r squared. The x is a 4r cosine theta. The x is an r cosine theta multiplied by 4. And so now I have this equation. So I just converted it. And if I move that over, r squared equals 4r cos theta. you know, I'm trying to solve for r, and it's dangerous to do this with variables, but we do this in polar coordinates. I can divide by r. Dividing by the variable is sort of dangerous in algebra. You tend to lose answers. But for the purpose of converting here, I can divide by r. I can divide by r, and I just got myself this equation. R equals, I got one r here, equals 4 cos theta. So that's cool. I just converted this equation into polar coordinates. And this is kind of a famous one too. This is a circle. And you know, we could have completed the square. Maybe we would have realized this is a circle. And just to quickly tell you what it is, this is a circle centered over here at 2 with a radius of 2. So it's tangent to the x-axis, y-axis here. Radius of 2 centered off here at 2 on the x-axis. And that's, if I would have completed the square, I would have saw that here. So that's kind of a famous polar equation. We have this famous polar equation. There's another one. These off-centered circles. This circle's centered at the origin, but this off-centered circle is kind of famous polar equation. All right, I'm going to keep talking here. One more converting problem for fun. What if I have r equals secant theta? So now I'm in polar coordinates. What the hell is that? And maybe I want to convert to rectangular to see what it is. Well, let's play around here. You know, a secant is a 1 over cosine. If I multiply by cosine, r cosine theta equals 1. I just multiplied by cosine, doing a little algebra. And then, according to converting back and forth, r cos theta is an x. So that's x equals 1. So guess what this is? This is a vertical line over here at x equals 1. I mean, that's what this is in polar coordinates. A vertical line at x equals 1. I mean, you could plot different thetas. At some point, theta is undefined, you know. Theta is undefined when the equation is undefined when theta is pi over 2 or negative pi over 2. So if you plot different thetas, you get these different points. You know, what if you plotted 89 degrees? That's pretty steep. That's very steep. But as soon as you get to 90 degrees, it's undefined. So if you're plotting these values with these thetas between negative pi over 2 and pi over 2, you plot out this infinite vertical line, I guess. That's pretty wild. Okay. Just playing around converting. Then what happens in 10-4 then is we learn some famous polar shapes. And so we've already stumbled across a couple, the circles. The centered at the origin circle, that's easy, and the off-centered circle. And we'll may review those again a little bit. But then there's this whole class of things. There's these limicons. That's a French word, and that's a little accent or cedilla, I think they call it, underneath the C. I think it makes it a soft C. Not that I'm a French expert, and they all look like this. R equals A plus or minus B sine theta, or R equals A plus or minus B cos theta. And by the way, this is where you can plot points, but at some point it gets a little fun to use your graphing calculator. You can put your graphing calculator in polar mode, and then instead of y equals, it says r equals. And when you hit your variable button, instead of x, it's a theta. And it works well in polar mode. You got to set your window for theta and so forth. But it turns out these limicons look like this. There's this kind of a limicon. And it comes in here to a point. And technically, that's called a cardioid. Maybe you see why. It's called a cardioid. It looks like a heart. That one happens to be kind of upside down. They can sit vertically like this, right side up, upside down. They can sit horizontally, okay? Here's another one. This is another limicon. This is one. I'll do this one this way. This time it doesn't come to a point. It actually also goes in and does a little inner loop. So this is a limicon with an inner loop. This is just a cardioid. Comes to a point there. There's another one. Let's see here. I'll do one like this. There's one that does a little dimple. That's what the book calls it. The book calls it a dimpled limicon. And there's one more. They call it convex. I'll do it over here, where it doesn't really dimple. It just sort of flattens out, and it's probably not exactly totally flat like that, but it kind of flattens out. It's not a circle. It's a, but these are some famous polar shapes. They're all called limicons, but I called that a cardioid, a limicon with an inner loop, a dimpled limicon, and a convex limicon. I don't care too much about the words, but it helps distinguish them. They all come from these equations. You know, the ones with sine sit vertically, so this one would involve sine, these two would involve sine. The ones with cosine sit horizontally, that would be these two. So it could be either one. And then the book talks about how the ratios of A to B help decide which is which. So depending on the size of A and B. Now I don't care for you to memorize that. You can look at it in the book. I could mention it here. I think this is when A equals B. You get this. I can't remember. Maybe when the ratio of A is less than B. I could look here in my book. I don't. The ratio of A to B is less than 1. That's kind of what I said there. This is when the ratio of A to B is between 1 and 2. And this is when the ratio is greater than or equal to 2. Huh. So yeah, anyway, the ratio of A to B. The size of those numbers makes you have these different shapes. But you don't have to memorize that really. You could sit here and plot points. You can also use your graphing calculator to see this. You know, in order to plot a full picture of this out, you let theta go from 0 to 2 pi. Kind of makes sense. So that's a big special category of polar graphs, special polar graphs. There's a nice chart in the book in section 10 for it. Let me say a couple more. There's these roses, and this is outlined in the book as well. These are R equals A cosine n theta, or A sine n theta. So this is when you usually have a multiple of an angle, like a 2 theta or a 3 theta or 4 theta, and you get these roses. They look like this. Actually, they look more like daisies than they do roses. That's an example of one. What they say is when n is odd, then you have n petals. So when n is odd, like 3 or 5 or 7, you have 3 or 5 or 7 petals. When n is even, then you have 2n petals. So if n is a 2 theta, you have 4 petals. And again, the cosine or sine kind of rotates it a little bit, depending on if it's cosine or sine. And this A is sort of the length of the petal, the extreme length of the petal here. The petals are evenly spaced apart, so this one is at 0, this one's at 120 degrees, 0 degrees, 240 degrees, 360 degrees, you're back there. I could also talk in radians, of course. So cool. Roses. One little caution. With this odd-petaled rose, you only need theta to go from 0 to pi. To plot it out, you only need theta to go from 0 to pi, plots out an odd-petaled rose. For the even-petaled rose, you need theta to go from 0 to 2 pi, like our previous graphs. It's interesting. From 0 to pi, it plots out the entire rose for an odd-petaled rose. You know, earlier, I've got a lot going on here today, but a little earlier I had this graph. And that was, I called that an offset circle. It's a circle radius 2 centered off there on the x-axis at 2. You could also, funny thing is, you could think of it as a one-petaled rose. You know, n is 1. Anyway, it's one big fat circular petal. But it's a circle. It's not a one-petaled rose, that's just me. But it does follow this rule that only theta goes to plot that out. You don't need theta to go from 0 to 2 pi. You start here with theta equals 0. It plots these points. When you get here, you're at theta equals pi over 2. And when you start plotting these points, you get these negative values of r. And so by the time you get to theta equals pi, you've plotted out the whole rows. So that applies to that too. That's important because the next section we start trying to find the area of some of these shapes, and we integrate. And when we set up an integral, we need the bounds of integration. And you might just automatically say, oh, I'm going to go from 0 to 2 pi. Well, then you're going to get double the area. So you've got to watch out for these subtle, how much theta it takes to plot this out is sort of important. All right, this video is getting a little long. There's more to say in section 10.4. And then, like I said, 10.5, we start trying to do area in polar coordinates. And then this course is about over. But keep doing some homework.